Welcome to a new lesson. In this lesson we'll be discussing rational numbers. Before we discuss rational numbers, let's review all the other number types. The natural numbers are the numbers you are using every day. These numbers include values from 1 all the way up to infinity. The numbers you can count with your fingers and toes are all natural numbers. For example, 1, 2, 5, 18, 150, and so on are natural numbers. Whole numbers are just like natural numbers, except that they also include 0. Did you know that ancient mathematicians worked for a long time before they used the concept of 0? Eventually, they realized they need a value that represented no value at all. So whole numbers are 0, 1, 2, 5, 18, and so on and so on. If you look at the number line, whole numbers are natural numbers including 0. Integers. Did you notice how these numbers lines all started at 0? Numbers lines with integrals, so integers, can have every positive and negative number. When we put in the negative numbers, we made the set of integers. Integers include all the numbers from negative infinity to positive infinity. So there are whole numbers, natural numbers, and negative values that are whole numbers, are integers. Rational numbers. Those are difficult to understand. You probably heard of these before. Another term for a fraction is a rational number. The word rational comes from the word ratio. In the case of rational numbers, it is a ratio of two integers. The integer on top is called the numerator, and the integer on the bottom is called the denominator. There's an extra rule you must remember. The bottom number can never be 0. If there is a 0 on the bottom, the division doesn't work. We'll get into the math of fractions and decimals in other sections. Just know that the rational numbers is one integer on top of another in a fraction. I want to give you a fast example. 1/3. We have an integer on top, a denominator, and a numerator. So on top is numerator, bottom is denominator. And if you put this as a decimal form, we have 1.333 repeating. This 3 goes on forever and ever. A different definition of rational numbers is a decimal that is constantly repeating itself. And there's a specific repetitive pattern. Not really a repetitive pattern, but repetition. In this case, the 3 is repeating. For example, if we have 4 9ths, again, it's a rational number. 4 is the numerator, and it's an integer. 9 is an integer, and it's the denominator. And when you put this in decimal, 0.444, 4 is repeating. 4 goes forever. So that is a rational number. Now let's start with our irrational numbers. What's that? That's all the other numbers. Number is irrational if there are infinite, non-recurrent decimal places. That means non-repeating. Therefore, it cannot be expressed in the form of a fraction. The best known irrational number is pi, which is defined as the relationship between the perimeter of a circle and its diameter. Notice that there is no recurring repetition. Another example of this is root 8. If you plug this to your calculator, we get 2.828427125. And of course it goes forever and ever, but it doesn't repeat. There's no repetition. Therefore it is an irrational number. Most of the irrational numbers that we're going to be referring to will have the root involved. It will be cubed root, square root, or so on, other roots that cannot be simplified. Now let's take a look at all the numbers together. These are called real numbers. So we have natural values, we have whole numbers, we have rational values, and irrational values. So recall, Let's take a look at our natural values. These are 0, 1, 2, 3, and 4, and 5. Of course, we're still forgetting that there is whole numbers. And actually, I think we have to fix this little Venn diagram. It's called Venn diagram. This is actually referred to as whole numbers, not natural numbers. And natural numbers cannot include zeros. This is your natural numbers. So we have integers, and these are whole numbers, positive and negative. So I'm just going to write an I instead of a Z. All of these are encompasses with rational values. That these are fractions and non-fractions, and all of these have can be repetitive. And the last one, instead of I, we're going to use Q for a little line top of it. This is the irrational numbers. These fractions, these numbers cannot be written as a fraction, and they go on forever, and they do not repeat. And of course, everything else, actually everything goes under a real number. So all of these are real numbers. So using the knowledge of our types of numbers, we can answer the following question. Tell whether each number is rational or irrational. Explain how you know. So recall that rational number can be put as a fraction, and irrational is non-repeating and goes forever. Goes forever. So right away, A is going to be a fraction, so that is a rational. And let's take a look at B. It's root 14. If you type this in your calculator, we'll get the value of, I'm just going to change colors because I don't necessarily like red, 3.74165738 dot 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 dot. Notice there are no repeating values. It's not. It doesn't mean that 7 is here, 7 is there, 7 is there. It doesn't mean that they're repeating. I mean there is no specific repetition. There's no 741. There's no 741 repeating over and over again. That's why this is an irrational number. And let's take a look at B. C. That's what I meant. C. And we have cube root 8 and 27. You could plug this into your calculator right away, or you could simplify. Cube root of 8 and cube root of 27 is 2 and 3. So it's 2/3. And right away, you could see that this is a rational number because it could be put into a fraction with integers numerator and denominator. So the last question we're going to do is we're going to use a number line to order these numbers from least to greatest. So we have cube root 13, square root 18, root 9, 27 to the power of root 4, and negative 5 to root cube root. Now, what you can do is you could plug this in your calculator, and then the answers are quite easy. But what if you do not have a calculator? That would be a little bit of a challenge. We could start from the end, and what I'm going to do is just write out the cube roots for you. And I know 1 cubed is 1, and 2 cubed is 8. So therefore, roughly, negative 5, or actually 5, is somewhere between 1 and 2, so it's 1 point something. 1 point, it's closer to 8 than it is 1, so it's probably about 1.6, 1.7. And since it is a negative, it's going to be negative 1.6. So right away, we know that's going to be a negative value. How about 27? How about 27th root of, well, this root? You have to a little bit play around with this one. So we know 1 to the power 4 is just 1 times 1 times 1 is 1. What about 2 to the power 4? That's approximately 16. And 3 to the power 4, that's about 81. So since we have 27, it's going to be close to 16, and I presume it's going to be around 2.1. So right away, we know it's about 2.1, approximation. How about 9? Well, root 9 is just 3. 3 times 3 is 9. How about root 18? We're going to use the square root. I'm just going to isolate everything, and I'm going to change color. Root 18, so let's write out our perfect squares. 1 squared, 2 squares, squares, 3 squares, 4 squares, and 5 squares. So we know that 4 times 4 squared is 16, and 5 squared is 25. So 18 is going to lie somewhere between 4 and 5, square root of 18, and it's probably it's closer to 16 than it is to 25, so it's roughly going to be, I think, 4.1. So again, this is without using calculator. And the last one, or actually the first one, which is for us the last one, cube roots. Again, 1 cube, 2 cubed, 3 cubed should be enough for us. 1 cubed is 1, 2 cubed is 8, and 3 cubed is 27. Notice that our cube root of 13 is closer to 8 than 27, so I'm going to presume it's somewhere between 2 and 3, and it's probably going to be about 2.2 approximation. So I'm going to box these answers. And we're going to put this on a number line. So we know that we have negative 1.6 is to the left. Then the next smallest one is 2.1. 2.1, then 2.2. Don't forget the 3, and then the 4.1. And I'll just recopy what these are without approximation. So the first one was root 3 of negative 5. 2.2 was 27 to root 4. And 22 was 2.2, 2.2 was cube root 13. 3 was square root 9, and 4.1 was root 18. And since this is a number line, make sure you finished off number line with the arrows at the back and at the front. That means on the left-hand side and on the right-hand side. And here is our solution.